Okay, so going along in 10.1, we talked about linear regression and actually correlation, but 10.2 will take it a step farther and put the linear regression to go along with that. What linear regression is, we have paired data, and do the points have a linear relationship? Can we find an equation and line of best fit? Can we predict the value and the response variables and the new variables with the predictor variable? So in other words, can we use that predict something? What is the fractional part of the variability? Y is associated with the variability in X. So long story short, if they are linear related, can we come up with a line of best fit? So can we come up with an equation that represents this line? And then can we use that equation to predict maybe the future or some missing data points within our data that we came up with for our line? So here we go. Least squares criteria. The line that we fit to the data will be such that the sum of the squared distances from the line will be minimized. Let D equal the vertical distance from any point on the regression line. So here's some data. We have a blue line that was the line of best fit. Okay, so it's the best possible line because what it did is it took these points D, the ones that were plotted, not points D, but these pink fuchsia, whatever dots, and it calculated out the distances of the vertical distance from that point to a potential line, and there's your D. What we're trying to do is get the sum of those D squareds, and the only reason why we're squaring them is it's going to take out the whole negative concept because here distance is positive, here it's negative, positive, negative. We're going to try to get that as small as possible, and that's why you have what's called the least squares line. Okay, now we call it the line of best fit, or you could call it linear regression. All kind of meaning the same thing. So we have y hat equals, that's what that means, a little top part to it, y hat equals a plus bx. It's not quite slope-intercept form. They use a little different method, but where a is the y-intercept, so where it crosses the y-axis, and b is going to be the slope of the line, so rise over run type of stuff. Okay, finding regression equation. This is in your calculator, sorry, it's in your book, but I'm going to read through it here real quick and kind of skim through it. Obtain a random sample of n. Again, n is the number of ordered pairs you've got, where x is the exploratory, y is the response variable. The data pair should follow a bivariate normal curve. So basically, it's a two-variable normal curve. It helps us out with a lot of other things. Okay, the mean of the fixed line values of x and y values should be normal distribution, should be mound-shaped or symmetric. And for a fixed y and x value should have their own approximate normal distribution, blah, blah, blah. So from your x's, we can compute the sum of x, sum of y, sum of x squared, sum of x, or y squared, sum of xy. And we can also find your means of those two as well. Again, put x into list 1, put y into L2, run 2 var stats, and I think I might have this backwards. It might be 1 var stats. Try them both out. Okay. And figure out all those values. I don't want you to do them by hand. With n equals the sample size, you can find the slope by this formula. Okay. Again, you've got those values known to you. You can plug those in. Now, once you have the slope, you will take your average for x and y, and you're going to plug them in for x bar, y bar. You'll get this number, and you can solve for a. It's like taking a point on a line, putting the slope in there, finding the y-intercept, and then you can take a, put it back in, take b, put that back in, and you've got your equation of least squares, or line of best fit, or linear regression. Again, they're all synonymous. They all mean the same thing. So here we go. We got x is the size of caribou population in hundreds. Y is the size of wolf population in Denali National Park. Here's your x and y as an ordered pair. That would have been 30, 66. Put your x's into L1. Put your y's into L2. Run your 1 var stats or 2 var stats, whichever one it works out to be. Get all those values. And we're going to find the sum and the y-intercept while we're at it. Okay, take the appropriate values from your calculator, put them in the correct spots. You're going to be finding the slope here first, n again is 7 because there were 7 ordered pairs. Work that out, and you get a slope of 1.6. So that's why there's a 1.6x in my final equation. I'll take my x bar, I'll take my y bar, and I'll take this b, and I'll plug it in here for y bar, there for x, and there for b, and that's how I get the y-intercept of 22.35. So my line of best fit is y hat is approximately 22.35 plus 1.6x. Okay, so using that regression line. So here's what we can do once we finally got that regression line. Remember, x bar, y bar is always going to be a line that's on that best fit. Also, the slope tells us whether or not there's an increase in the exploratory variable by 1 unit. And here's what this basically means. Is going back to this, is there is an increase of 1.6 wolves per 100 caribou. Okay. Oh, yep, wolves. So there's 1.6 wolves, excuse me, per well, because it's in hundreds, per 100 caribou. Okay. So rate of change. So as the wolves increase, so does the caribou. Makes sense. It's probably the fact that the caribou are the food. To make a prediction, okay, there's 2 ways. Well, not one, 2 ways. We're going to take an x value and we're going to plug it into our equation for x, and it's going to calculate out some y. There's 2 ways to look at this. It's either interpolation or it is extrapolation. Interpolation is predicting y hat values or y values for x that are already between the x values that are in our data set. So if I go back to our caribou, I've got from 17 is the low end and 34 is the high end. So if I wanted to plug x is equal to 33 into my equation, that's interpolation because it is between the numbers 17 and 34. Extrapolation would be predicting a y hat value for x values that are beyond or before our data. So maybe I want to predict x is equal to 40. Well, that's bigger than my biggest number of 34, so that would be extrapolation. Maybe I want to go x is equal to 15. That's smaller than 17, so that's also extrapolation. It's out of my data set that was given to me. Extrapolation can be tricky because you don't want to pick a value that's too far away from your original data set, because then my response isn't going to be as reliable. My data that I use to get this line is for only so many certain x values. I can't go too far out. So caribous and wolves example, for example, I want to figure out x is for 2100. So I'm going to put 21 in for x, do the calculations to get 55.94 or 95 wolves. So using my line of best fit, my model, for 2100 caribou, there's about 56 wolves. Now, this is going to be extrapolation. I believe, because, well, here, I better double check. No, it's not. I take that back. I think my largest number for my wolves was 34. So our 21 is within that. Oops. So that's actually interpolation. Okay. So here's why extrapolation can be difficult. I use the example of, like, say, West Fargo's population. Let's say back in the 60s, they came up with some data for the population growth in West Fargo. They came up with a line of best fit, and they wanted to predict out to now. So they said, like, we started in 1960, so x equals something like 66. Plug in 66 for x, there's your given population. The only problem with that is there probably wasn't as much population growth in the 60s as there is now in West Fargo. So that data was good in the 1960s, maybe to predict the 70s, but not 66 years out. Okay. Coefficient of determination. Another way to gauge the fit of the regression line of the equation is to calculate the coefficient of determination as equals r squared. We can view the mean of y as a baseline for all the y values. So here's what we do. You've got a y var, and you can't really see that, but there's the baseline of y bar. That's what that means right there. So there's the baseline. What you can do is take a difference between each point above and beyond that blue line and kind of take the average of those. The total variation is between the y portion of this point and y bar. There's your total variation. That's kind of what that says. Again, this picture's in the book if you really want to look at a more crystal clear one. From what y bar should have been to where the line is, that's your explained deviation. This is the unexplained deviation. Deviation, remember, is about how spread out it is. So we're going to take to get the total deviation with a little bit of math here and theoretical is each y value you're going to take away the mean, each y hat you're going to take away the mean, each y you're going to take the mean, and you're kind of in a way finding the average of that. Okay. I can go into this a little bit more if you really want to know the theoretical, but basically what it comes out to be is that r squared is equal to the explained variation divided by the total variation. And that's one way to get it. Or if you know what the r value is, just square that number and you're good. So on the last notes, let's say r equals to 0.949. Square that number and you've got your r squared. And what r squared does for you is that it computes the sample correlation of the coefficient r, then compute r squared. There we go, what I just said. The value of r squared is the ratio of explained variation over total variation. R squared is the fractional amount of total variation in y that can be explained by using the line linear model, so your equation you came up with. So therefore, furthermore, 1 minus r squared is the fractional amount of total variation of y that is due to random chance or to possibility of lurking variables that influences. So let's say your r squared equals like 0.98. So 1 minus 98 is 0.02. 2% of the data or the results can be explained by some sort of lurking variable that was hanging out in the data. So the higher the r squared, or the closer it is to 1, the less crazy the data is, basically. Okay, so here you go. You got your assignment, page 614, 1, 3, 5, 9, and 13. They're all odds. I will show you some calculator tricks again to kind of help you out with some of these calculations.